Now, how do we really use this formula? Again, example is very helpful. And as always, we'll take our binary world. And if you remember, this binary dynamics is maybe a unimodal map. Dynamics are unimodal maps. So if you don't like maps, 3-disc billiard has binary dynamics. It's a very physical thing. And in that case, we can write the zeta function explicitly as 1 minus the weight of fixed point 0, 1 minus the weight of fixed point 1, 1 minus the 2-cycle weight of the 2-cycle, 1 minus the weight of 3-cycle, and so on. As each cycle carries with it z to the n or s, either way, s close to 0 or small z, whatever makes you happier to think about analyticity of the series. It's very natural to order this Taylor, this infinite product in terms of product of ones in all of them, and then the product just of this cycle with ones elsewhere. So that's 2, 0. It's a minus sign. Or this one. So these two guys are length 1 topologically. So that's what distinguishes them if you think of them as a Taylor expansion in Z small. Then this one multiplied by all the other ones. But then there is also a possibility of multiply these two guys and ones elsewhere. T0, T1. Then there's T1, 0, 0 minus T2 cycle, T1. And then we can go to the 4 cycles. And for example, there is a 1, 0, 0. They'll show up in a series. We can group the terms in such a way that that is what it comes with. Well, each prime cycle shows up only once, so that's the only thing that can happen. And so on. We can organize them this way. And if you expand this a little bit, you'll see that this can be mildly complicated. So maybe I'll just write one more term. So if I look at T0011 cycle, there are 3, 4 cycles. One of them looks like that. It'll show up shadowed by T001, 3 cycles times T1, minus T0, minus T0, T011, and then there will be plus T0, T01, T1, and this goes on. So there is a natural grouping into combinations, and this natural grouping is something we already noticed when we were discussing the just counting. So when we were discussing the transition matrix where the weight was simply 0, 1 and nothing so simple, multiplied by z to the length of the cycle. We already observed that there is a natural grouping, and depending on symbolic dynamics, see, there is a part of it that is not cancelled by anything. So there's always something which I'll call fundamental cycles. So we show for full binary dynamics that all these guys, at least in a 0, 1 weighting limit, everybody else cancels these are the only fundamental motion. I can go left and right, and everything else is combined from these things. Now in general, because we are computing the cycle weights on particular periodic orbits, these lambdas are smooth functions, periods, every is a smooth function of something. So in general, this doesn't cancel because it's something that's evaluated at 0 or on 2 shadows. In this case, they're quite far away. So these things don't cancel exactly, but they cancel to a large extent. And for that reason, one can separate this into a part which I'll call curvatures, Cn. So there is a part, for example, when we're looking at golden mean pruning, it turned out that one of these things was forbidden. So this was forbidden. So we got a different set of, we got 0 and 1, 0 as fundamental cycles. But the rest organizes into combinations of these shorter ones. So there is always a splitting when you have finite grammar into fundamental part and corrections which I'll call curvatures. Maybe it's a badly chosen word, but they just look like they're measuring the deviations from all the weights being equal. So curvature. Or you call them whatever you want to call them. So that's the fundamental insight about chaotic dynamics. Yes, there are infinitely many periodic orbits. Yes, they're infinitely complicated. Yes, the number is going exponentially. But when you look at zeta function, which we'll use to compute all long-term predictions of the theory, there'll be two parts of it. There's something that captures the important qualitative behaviors. So on this side I go that way and stretch, but on this side I go stretch and I flip. So for a unimodal map, this is very qualitative different. Even the sign of the Floquet multiplier is different. And everybody else is more or less a combination of these basic behaviors. And this is the main reason why we'll be able to, by computing short cycles, produce predictions for infinite cycles, because these guys will capture, and these corrections, when the systems are nice, they'll be dropping off exponentially or super exponentially in cycle length. So we'll only need a finite number of this kind of shadow terms to make our prediction. So that's the basic idea. Now suppose you do this. So you construct a zeta function. Constructing a zeta function means you have to find all periodic motions hierarchically ordered by their topological length. And for each one of them, you have to numerically compute the eigenvalues of its stability, its Jacobian. So the Floquet multipliers, of which this is just the expanding part, describe the stability of every solution. And then on each solution, you have to compute expectation values, so the average of whatever observable you're interested in on that solution. And you'll need to know also the period of each solution. So this information you have to compute. So there should be a table that has all the information that you need. And now, once you have it, you can compute cycles, prime cycles, weights, and pseudo-cycles.